going to try and finish this first part of the course and tell you the statement of the Kodaira embedding theorem, a couple of examples, and at least some sort of rough idea of how the theorem is proved, at least in some simple special cases. So the statement is this. So for a compact complex manifold M, the following are equivalent. First, that's the thing that we want, that M is projective. So it has a holomorphic embedding into projective space, or equivalently it's an algebraic manifold. And the second statement is, so that's going to be the criterion, that's hopefully checkable in a lot of cases, that M admits holomorphic line bundle L with a metric H of positive curvature. So it's a condition we discussed last time. So that the curvature form of H is positive definite. So so this is a slightly mysterious statement on the face of it, because I guess that's not a bad thing if you're stating a theorem, if it sounds a little bit mysterious. So that doesn't give you a clue how you would cook up the projective embedding from the line bundle, the way it's stated. So we're going to state a more precise version later on that makes us more clear how the embedding is supposed to come from the line bundle. So first of all, I'm just going to try and reformulate the theorem a little bit and give you a couple of applications and examples how this can actually be applied. So the first remark is that so the theorem is sometimes phrased in terms of Kähler forms. So I don't really want to get into this today anyway. I'll just write it down quickly. So a Kähler form is just something like this. It's a closed 1-1 form that is positive definite in the sense that we introduced last time. So whenever I restrict the form to a complex line in one of the tangent planes of the manifold, then I get like a positive multiple of the preferred area form on that complex line. That's sort of picked up by the complex orientation. Closed 1-1 form. Omega. So certainly any omega h like this is going to be a Kähler form. But it's a particular kind of Kähler form. It's one that's also the curvature form of a line bundle, meaning that the cohomology class that it represents is up to this factor of 2 pi, the first Chern class of the line bundle, which, as we know, is an integral, lies in the image of the integral cohomology and the real cohomology. So then that turns out that that's actually a fact that this condition 2 can be restated equivalently, and this is how many people think about this condition normally, that M admits a Kähler form, so it's a Kähler manifold, omega such that omega lies in the image of the map from integral to real cohomology. So that's what used to be called the Hodge condition. So in the old times, Hodge manifolds, manifolds with integral Kähler classes. So this equivalence is not entirely obvious. I mean, so this implication is kind of clear from the definitions, but the reverse is not so obvious. I mean, so if you have a Kähler form representing an integral class, how do you make sure that that class is actually the first Chern class of a line bundle? That's something called the Lefschetz theorem. It's not particularly hard, but it's a sheaf theory argument, so I'm going to skip that here. So Lefschetz theorem on 1-1 classes. But more interestingly, talk about applications of Kodaira. So the first and nicest application is that every Riemann surface is algebraic. Every compact Riemann surface is algebraic. And, well, so what you do is any Riemann surface has complex any Riemann surface has complex hypersurface. You just take a point. It's going to give you an associated line bundle. It's pretty good already. You know that the first Chern class of this guy is actually Poincare dual to the point. So you know that the first Chern class is actually sort of the preferred generator of the integral cohomology. So C1 of L. So the positive generator. H2MZ. I mean, H2 is just, for a Riemann surface, it's just a top degree cohomology, so this is just a space of volume forms, basically. It's a statement that the first Chern class integrates to 1 over the Riemann surface, corresponding to the fact that I've taken a single point here. So that's a positive class, certainly. I mean, we can't quite apply the Kodaira theorem as I stated it here, because this is talking about actually finding a Hermitian metric of positive curvature on the guy. I mean, there's certainly positive forms in that class. You just take the area form. It's a positive form. But the question is that actually the curvature form of a metric on the line bundle? So every representative of C1 of L. So that's actually true on any Kähler manifold. That's the sort of thing I used last time to sort of give the sketch argument that the Chern classes determine the line bundle up to holomorphic isomorphism. Is equal to omega h for some metric h. On L. So I told you last time that in general, if you want to prove that on a Kähler manifold, you need the del-del-bar lemma. But on a Riemann surface, that's actually pretty simple. So you can avoid all the complications of the del-del-bar lemma. So on a Riemann surface, this is pretty easy. what do? You take omega in C1 of L, maybe in 2 pi C1 of L. So that's the thing that you want to realize as the curvature form of your line bundle. That's a line bundle, so it has Hermitian metrics. That's trivial. You take any Hermitian metric, and then you try to improve it to have the right curvature form. So take H tilde, any Hermitian metric on L. And how can you improve a Hermitian metric? Well, you can multiply it by globally defined positive function. Try to find H, so it's e to the minus psi times H tilde. So that omega sub H is actually equal to omega. Right, so that's the curvature form that you want. That's the Hermitian metric that you're looking for, and you can reduce that to finding one scalar valued function. That's the equation you want to solve. But that equation, by the definition of the curvature form, this is just equivalent to saying that, take dd bar log. It's just saying that omega H tilde, the curvature form of the given metric, plus id bar psi is equal to the curvature form that I want to have. So that's the PDE that you need to solve. So in general, that comes down to the dd bar lemma on KLM manifolds to finding solutions to that. But on a Riemann surface, del del bar is just a Laplacian. So that's solvable for psi on a Riemann surface. Why? I mean, so if you bring this guy to the other side, you're going to have the difference between these two forms, but they're representatives of the same class of 2 pi times the first Chern class of the line bundle. So meaning that difference is 0 in cohomology. So if you integrate the difference, you get 0. So all you're doing is you're solving the Laplace equation where the right-hand side has average 0, and that can be done uniquely modulo adding on a constant. So it's just a Laplacian. Okay, so modulo this teacher that you have to know how to solve the Laplace equation on a Riemann surface. So unique solution, modulo additive constant when the right-hand side has a mean value 0. So algebraicity of the Riemann surface comes out of the Kodaira theorem. Yeah, but you need to be able to prescribe curvature. So then, just write this down. So it's just an application of similar spirit for those of you who care. It's for higher dimensional KLM manifolds. That's an argument that tends to get used quite often. It's sort of in the same spirit. It's sort of saying, I mean, basically the reason why this argument worked is that the second cohomology of a Riemann surface is so small. Over the integers, it's just a copy of the integers. And that's something that you can use in higher dimensions as well sometimes to sort of quickly say that the manifold has to be algebraic. So compact KLM manifold. So just for those of you who already know this, with H20 equal to 0 is algebraic. And why is that so? The Hodge decomposition tells you if this Hodge number vanishes, which means that the manifold doesn't have any holomorphic to 0 forms, then this means that H2 of MR, which is just it's the integral cohomology tensor for the real. So killing off torsion. This is actually equal to H11 MR. So for sure, I'm going to be able to find a Kähler form that's actually rational. And then I pass to a multiple and I get a Kähler form whose class is actually integral. So the point somehow is that Kähler forms live in here. So the set of all classes of Kähler forms is an open cone in this space. But that's just a piece of the cohomology of a Kähler manifold in general. So you have a 1-1 part, but you can also have a 2-0 and a 0-2 part. So if the space where the Kähler forms live is just a subspace in general of the whole second cohomology. And now it could be that that subspace is somehow irrational with respect to the integral lattice. And then you're not able to find any Kähler forms whose classes are anywhere close to being integral. But if so, if these other pieces, the 2-0 and the 0-2 part of the cohomology aren't there, then for sure, just by density of rational points, you have to be able to find rational points in the interior of the Kähler cone, and then you're going to get an integral Kähler class over this other formulation of the embedding theorem, you're algebraic. So that's very handy. Yeah?
I'm sorry, are you saying that lowercase h20 is uppercase h2 mr?
No, I'm so sorry. I mean, I'm using the Hodge theorem here. Okay, so that's saying that H2 of MR in the Kähler manifold splits up into three pieces. Complex cohomology splits up into three pieces: H20 of M plus H11 MR plus C really plus H02 of M. So as a complex vector space. And now these two guys are sort of complex conjugates of each other, and that space is invariant on a complex conjugation. So what I'm saying is if these two pieces aren't there, and that guy is just the lattice part of the integral cohomology, throw away the torsion. So this is H2 MZ tensor C complexified. Then I actually have to be able to find lots of rational points that come from the integral lattice inside the H11 part, simply because the H11 part is everything. Otherwise, there are these other pieces, and somehow the H11 part might be might sort of be skewed with respect to the integral lattice and not meet the integral lattice at all. Yeah? Oh, that's just a dimension of this guy. Yeah, that's just a dimension of this guy. Sorry. Yeah. And that you can compute often. That's a computable thing. And if that happens to be 0, you're done. You just know that the thing is algebraic. Well, not every Kähler form in H11MR, but if H11MR is the whole of H2, then you know the rational points are dense. So you definitely have to have rational cohomology classes in the interior of the Kähler cone, because the Kähler cone is an open set. So you definitely have a Kähler class that is rational, and then you just scale it up and it becomes integral. So H. Okay, second application is to complex tori. I'm just going to state the result. So you can imagine for complex tori, everything reduces to something you can state in terms of linear algebra. So a complex torus, so will be Cn mod lambda for lattice lambda. It's a free abelian group isomorphic to Z to the 2n. Is algebraic. if and only if there exists what is called a Riemann form. For this lattice lambda. And the Riemann form is just a Hermitian inner product on Cn, whose imaginary part takes integer values on the lattice. So it's a Hermitian inner product on Cn. Such that the imaginary part of uv is an integer for all vectors u and v in the lattice. So that's what the Kodaira condition boils down to. And I mean, not surprisingly, in complex dimension 1, so for elliptic curves, you always have a Riemann form. That's pretty easy to see. So if you take n equal to 1, so you can assume that your lattice has the standard form, so it's just z plus z tau, where tau is in the upper half plane. And then you can just let the Riemann form be, so it's a Hermitian inner product on C. So up to a scale, it has to be the same thing as a standard Hermitian inner product, just z times w bar. And then you normalize by the right scale. So the right scale is the imaginary part of tau. And then it's an easy exercise to check that the imaginary part of this thing only takes integral values if you plug in lattice vectors. Because of this normalization, you're dividing by m tau. So what happens for higher dimensional complex tori is also pretty interesting. At least in dimension 2, you can sort of visualize pretty well what's going on. I mean, it's not easy to see. You need to work to get to this picture, but once you're there, it's actually pretty clean. So tori when n is equal to 2. So if the idea is that you have the space of all possible complex tori, and that's just huge, and there's sort of tiny subspaces in there that correspond to algebraic tori, and the generic complex torus is not going to be algebraic. But so if the exact picture is pretty clean in dimension 2, so you have this big space. That's the space of all complex tori. So what is that? A complex torus is given by a lattice in C2. Lattice is given by its generators. And the generators are just the basis, so it's 4 vectors, just the basis of C2 over R. So every basis of C2 over R, every basis of R4 is going to give me a complex torus. So I have like a GL4R acting on this thing. And then I'm asking, when are 2 bases going to give me the same complex torus up to isomorphism? Well, it's just if they differ by a matrix in GL2C. That sort of preserves the complex structure. So the space of all complex tori is actually GL4R, modded out by GL2C. So it turns out that's a complex manifold of complex dimension 4. So this has complex dimension 4. Honest to God complex manifold. And now, so if you could ask, so where are the algebraic tori in there? And the claim is they're going to be complex hypersurfaces, but there's many of them. Because the statement here is that whenever I'm able to find a Riemann form, I know that my torus is going to be algebraic. But there are sort of countably many possible Riemann forms in a sense, and each of them corresponds to sort of one family of tori that this particular Riemann form makes algebraic. So there's actually sort of countably many families in there, each of which corresponds to sort of algebraic tori with like a fixed Riemann form, basically. The picture is that, you know, this space is actually filled with complex hypersurfaces, and they're dense. There's countably many, but they're dense, so they're like Q and R. Sort of algebraic complex tori with a fixed choice of Riemann form. So this is like it's a countable dense union of complex hypersurfaces. And each of these guys, so you have to think about that. But you can give a similar description as a homogeneous space, but now you have to talk about maps in GL for R that actually preserve a Riemann form. So it cuts down from GL for R to the symplectic group for variables, because Riemann form isn't this Q-symmetric form. So this is actually SP for R modded out by U2. That's a complex manifold 2 of complex dimension 3, and that's what people usually call the Siegel upper half plane in genus 2. So it's sort of the natural generalization of the usual upper half plane to from complex 1 tori to complex 2 tori, except that, you know, now the difference is that it's no longer true that all complex 2 tori are algebraic, but the Siegel upper half plane only parameterizes of the algebraic ones. Plus there's now lots of different possible choices for Riemann form. And then so you might ask, well, you know, how can I see the non-algebraic guys? Is there any way of describing them? And so what's actually true is that it's copies of the Siegel upper half plane, countably many, and the union is dense. So there's only one complex direction left, and I'm claiming that through every point and for every choice of red hypersurface, there's a copy of the Riemann sphere. There's a copy of CP1 in there, a holomorphic copy of CP1 that sort of parameterizes the transverse directions to some extent. So there's sort of a transverse P1 in this space. So you have this P1. That's a sphere, so of parameterizing complex structures. And the way you picture this is that, you know, you have the rational points, the points with rational coordinates on the sphere that correspond to algebraic complex structures. Then you have all the other points, the irrational points, and those are non-algebraic. And if you want to know sort of what is this sphere, we're in complex dimension 2, so we're in real dimension 4. So we have quaternions. So this is the unit sphere in the space of imaginary quaternions. So you have one complex structure that corresponds to I, but then you can replace it by J or K or any other point on the unit sphere in the imaginary unit quaternions. This is So then let me just give this sort of more precise restatement of the Kodaira embedding theorem that sort of relates the line bundle directly to how the embedding is constructed. So I mean, the idea is, as I said a couple of times, that you want to produce lots of holomorphic sections of your line bundle, maybe of a tensor power of your line bundle, and then use those holomorphic sections to construct your embedding into Pn, sort of generalizing how meromorphic functions can give you maps to P1. It's sort of kind of useful to introduce some terminology for those kind of maps. So you have compact complex manifold. L to M holomorphic line bundle. And I'm going to call V the space of global holomorphic sections. So because my manifold is compact, that's a finite dimensional vector space. And most of the time it's finite dimensional for a pretty obvious reason, because it's zero. So we're interested in the cases when this is not zero. Okay, so some terminology. A linear system relative to this line bundle is a linear subspace. W inside V. Okay, that's a pretty silly name, and I mean the idea is that you have a picture in mind sort of associated with that linear subspace. So I mean, if you're talking about a linear system, what's the picture you have in mind? Is that the family of hypersurfaces S inverse of 0, where S is in W. So W is a space of sections, and you're just looking sort of at the family of all of the zero loci of these sections as they sort of sweep out your manifold. It's sort of a parameterized family of hypersurfaces. And the parameter space is W, but actually any two sections that just differ by a non-zero scalar are going to give you the same hypersurface. So actually the parameter space is a projective space. It's a projective space of W. So you think about sort of a compact family of hypersurface sort of moving around in your manifold. And you say that the linear system is complete if W is V. So if it's the whole space of sections, and you say that it's a pencil if the dimension of W is 2. So then pencil just means this is like a one-parameter family of hypersurfaces. So like, I don't know, all quadratic curves in the plane that pass through two given points, something like that. Family of hypersurfaces, so it depends on one parameter. That's a pencil. So then, so the base locus. So I mean, obviously, you're going to have the same issue with indeterminacy of these maps as you had for meromorphic functions. I mean, the problem is if all sections of your line bundle, or at least all sections of your linear system, vanish at some given point, then this Kodaira map wouldn't make sense. I mean, Kodaira map is to take a bunch of sections and I take them as entries of like a homogeneous coordinate vector in projective space, so they can't all be zero. But that can happen, certainly. And that's the points where that happens is usually called the base locus, or sort of indeterminate locus of your linear system. So this be S of W, that's the point set of all points in M, where for all S and W, S of P is 0. Third, the Kodaira map. So it's phi W goes from M minus the base locus to, so I'm not going to use homogeneous coordinates. I'm going to write down the Kodaira map in invariant ways. I'm not going to be using homogeneous coordinates on my target space. So that's a target space, the projective dual space of the linear system. So that sends a point to what? To the linear form maps a section to its value at that point. So W is a space of sections. W star is the dual space. So an element here is a linear form on sections. And what is that linear form? I take a section, I evaluate it at a point. And then, I identify two of these. I take the projectivization, so mod out by multiplication by non-zero scalars. So that's like a universal construction. You can't just you can do that with holomorphic sections, but you can also do that with harmonic functions or eigenfunctions of the Laplacian on a manifold. Like this is some sort of universal thing that you can use to construct interesting embeddings of manifolds. So I think this plays some role in minimal surface theory or minimal submanifolds to construct embeddings, minimal embeddings into Euclidean space, but sort of, or minimal embeddings into the sphere or real projective space using this sort of formalism. So then we say that the linear system is very ample if it doesn't have any base points. And the Kodaira map is an embedding. It's a globally defined map and actually an embedding into this target space. The line bundle is called very ample. If the complete linear system is, and L is ample, if L to the K is very ample for some sufficiently large power K. And since sort of the more precise restatement of the Kodaira embedding theorem is that ample and positive line bundles are the same thing. Kodaira. So it's a more precise statement. So if you have a positively curved line bundle, then it's actually going to be true if you pass through some sufficiently high tensor power of the thing, then it's going to have sufficiently many sections that there is no point in the manifold where all of them vanish, first of all, so you have a well-defined map into projective space, and second of all, that map is actually holomorphic embedding onto its image. And this is how you get the algebraicity that's claimed in Kodaira. Okay. Um, I'm going to give you a couple of examples, just need to get more familiar with this terminology. The line bundles O of k on projective space are all very ample if k is positive, so OPN. It's very ample. And the associated map, so the Kodaira map, goes from Pn to, so basically you're using all degree k homogeneous polynomials in order to embed your thing. So I think the right dimension is n plus k over n minus 1. So it's called the Veronese embedding of projective space. So clearly when k is 1, this is just the identity. If you want an automorphism of projective space, if you don't want to make any identifications. So for example, when n is 1 and k is 2, then this is what Jacob was talking about at some point. You're embedding the Riemann sphere as a quadric in P2. When n is 1 and k is 3, you're embedding the Riemann sphere as a curve in P3, as a curve in 3 space. It's a pretty interesting curve. So that's a curve in 3 space, so that's codimension 2, but you need 3 equations to cut it out. So that's the example that I actually wanted to use on the first problem sheet. Thought I had an easier example, but I shot myself in the leg. So the images of these Veronese embeddings are sort of, even though the domain is very simple, the image is sort of very interesting, usually from the point of view of submanifold geometry. So some pretty complicated image. So the second example is if you take a line bundle on PM cross Pn of bi degree k and L. So by definition, this is just you pull back OPM of k from the first factor and tensor it with pullback of OPN of L on the second factor. So this is always very ample if k and L are positive. There's an interesting special case here that I mentioned once before. If k and L are both 1, and this is what you call the Segre embedding. Goes from Pm cross Pn. If you work it out into P Mn plus M plus N. And that's sort of the embedding that shows you that the product of projective spaces is again projective if you didn't already have the Kodaira embedding theorem. So it tells you hands-on that the product is projective again. So third example, elliptic curves. Then you look at the line bundle associated to a point. You're saying the line bundle associated to a point is pretty boring because it has only one section. If you have only one section, you can't embed into anything. You just map to a point, like the Kodaira map goes to a point. It's not actually even defined at the point itself formally. So the line bundle associated with a point on the elliptic curve is kind of boring. If you take the line bundle, if you take its square, and so you have two sections, so you get a map to P1. It's a degree 2 map. So you could say that that's a pencil. The image is P1, so it's just a meromorphic function. And this is the Weierstrass P function. It's an elliptic function. And if you take one more power, then the thing actually becomes very ample. So I mean, this is clearly not an embedding. It's a branched degree 2 cover. So if you take one more power, then you get an embedding into P3. Sorry, P2. That's an embedding onto a cubic curve. But all of these things take actually work to figure out, because Kodaira only tells you that there is, if you have a positive line bundle, and we've checked that this guy is positive, then some sufficiently high power is going to embed your space as something into some projective space. But if you want that some relatively low power embeds your thing as something specific in a low dimensional projective space, that's usually a lot of hard work to actually check that that's true. But these are sort of very classical maps, or very classical realizations of elliptic curves, of complex tori. So it's going to give a couple more complicated examples, but I think I have 10 minutes left, so it's probably better if I just say something about the proof of the embedding theorem instead, just to give you an idea how that works. So ask me if you want to see more examples. Okay. So that's, the proof that I'm going to talk about is not the original proof of Kodaira. That was very algebraic. So you use a heavy dose of sheaf theory. It's a much more analytic proof. I would have liked to have more time to say more about that. That's quite nice, actually. So the idea is really geometric. So it is to look at the local model. So you assume you have a line bundle with positive curvature, and then you want to know, what do holomorphic sections look like geometrically? So first of all, you make a local model. So if you want like a model space of constant curvature and study that. And the local model has absolutely no topology, like in Riemannian geometry. So as the underlying manifold is just Cn, it's not even compact. The line bundle is the product line bundle. So there's no Chern classes or anything. And all the non-trivial information comes from the metric, comes from the fact that you have a metric of positive curvature. What's the Hermitian metric going to be? That's just e to the minus, alpha over 2 times mod z squared, Euclidean radius squared. you know, Z is the base coordinate, W is the fiber coordinate. Alpha is a positive parameter. Then if you compute the curvature from omega h, so it's minus IDD bar log of h, then this is actually going to be alpha times I over 2 times the standard Kähler form on Euclidean space. So the sum dzk, which dzk bar. If you don't like Kähler forms, just imagine n is equal to 1 and there's just the standard area form on the complex plane. N equals to 1 is a perfectly good test case. So all the complications are there when the dimension is 1. And the picture is there and it's complete when the dimension is 1. And now the big question is, it's supposed to be a local model for what, holomorphic sections of positive bundles look like. So the simplest model for a holomorphic section you can take is just a constant section that's constant equal to 1. Take the trivial section. This is positive, and you can tune the parameter to make it more positive if you like. So model section is just S constant equal to 1. And now the question is, what does this thing look like geometrically? So I have a metric, so what I want to do is I want to graph the length of the section with respect to my metric. So the metric picture is that so this is Z, this is h of s comma s, so the length squared of the section. It's a Gaussian. Right, so because I want the curvature to be positive, I had to take a minus c squared in the exponent here. So this means the length of the section actually has this Gaussian profile as I go away from base point. So that's somehow the geometric picture that you should have. If you have a line bundle with positive curvature, with sufficiently positive curvature, meaning if you make this alpha sufficiently large, then it has lots of holomorphic sections, and you can imagine that they're peaked everywhere. So pretty much at every point of the manifold, there's a little Gaussian peak corresponding to a holomorphic section. I mean, the space of holomorphic sections is going to be finite dimensional. I mean, it grows with the tensor power. It grows as the curvature gets larger. So, I mean, there's some finite width to these peaks, so they overlap. So it's not an infinite dimensional space, but you've got these peaks pretty much everywhere. And you can use that to show that the Kodaira map, at every point I can construct a holomorphic section that doesn't vanish there. So therefore there's no base locus, and I can also use that to show that the Kodaira map is injective and has injective differential and that sort of thing. That's sort of the geometric picture. If the curvature was negative, I would have a plus sign there, so it would be a Gaussian like with a plus sign in the exponent. So just blow up as I go away from one centered point, and I would have no control what the section does as soon as I go a little bit away from my base point. So I've just no idea what's going on. Whereas here I expect sections to be localized in this way. So then that's just a picture, but how do I turn that into a construction? How do I sort of turn that upside down and construct holomorphic sections? So I take my line bundle, I trivialize it locally. So F is U cross C. That's my trivialization. I claim that I can choose F such that I pull back my Hermitian metric. That's just going to be e to the minus phi times mod w squared, where w is a fiber coordinate. I'm claiming that I can choose this trivialization in such a way that phi of p is 0 at my base point, so that's the neighborhood of p. So just at one fixed point, the differential of phi is 0. So I'm choosing like normal coordinates for my line bundle metric, and actually, phi is roughly equal to mod z squared over 2, where z are local coordinates on the base. Such that z of p is 0, and such that the curvature form of h can be written as, at that point, can be written as I over 2 times, so the standard Kähler form. Yeah, so I'm trying to get some sort of best possible approximation by the local model. And then what I do is on my original manifold, I take a cutoff function, something that's a bump near my point. And push forward so the standard model section so it's going to be a section of L to the K. So basically what I'm saying here is I'm not taking the section that's constant equal to 1. What I'm taking is I scale it up. So multiplying the curvature by K corresponds to raising the line bundle to the kth power. So I'm introducing another factor of K in front of the exponential, so this profile gets even sharper. And then I have to scale this thing up roughly by K to the n over 2 to make the L2 norm equal to 1. So I want to have a Gaussian with L2 norm equal to 1. So I take that, I glue that into my manifold with respect to my trivialization, and then I cut it off. And because of this Gaussian decay, the error that I'm making is not very big. So I'm creating a section that's almost holomorphic. And that's actually an almost holomorphic section. So if I call that S, then the L2 norm of S is going to be equal to 1, basically, because of, have a Gaussian that's scaled in the right way. But if I take the bar of S to check how holomorphic my section actually is, well, it's pretty holomorphic, except in the region where I've made the cutoff. But that region doesn't really contribute much because of the Gaussian decay. So this is on the order of, I guess, something like K to the n over 2 times e to the minus, 1 over 100 times K. So it's an almost holomorphic section. And now you sort of have to finish off with an analytic argument that tells you that if you have an almost holomorphic section, you can actually perturb it to become genuinely holomorphic. And this is where you use the positive curvature once again. And what you want to do is to solve the equation d bar s tilde equal to d bar s with estimates. I mean, looks like a silly equation to solve. I'm given s, I take d bar. I want to find s tilde so that d bar s tilde is equal to d bar s. There's a pretty obvious solution to this s tilde, so that's not the one I want. I know that this guy here is sort of exponentially small. And I want to find a solution that's sort of controlled by the right-hand side. I want to find a canonical solution, one that's given by sort of convolving with a Green's function, that sort of thing. So it's controlled by d bar s tilde, which is d bar s. And then s minus s tilde. The two guys have the same d bar, so that's a holomorphic section. But this is sort of the peak that I constructed, and this is the tiny little thing that has very small norm. So I'm taking the guy that I constructed, subtracting something off that has extremely small norm. So I get something that basically looks the same, but it's now genuinely holomorphic. And this step right here, so if you've ever seen the algebraic proof of Kodaira embedding, that goes through the Kodaira vanishing theorem that holds for positive line bundles, and this is sort of an effective version of the Kodaira vanishing theorem. That's basically saying that the line bundle doesn't have any degree 1 cohomology. That's an effective version of Kodaira vanishing. Okay, so if I'd had more time, maybe I'm going to do this on Monday actually, I would have liked to talk about how you actually prove these estimates. So of the analysis that's needed to prove these estimates. That's a pretty interesting computation. It's basically a Weizenberg formula, like a Bochner formula, like what Aaron is talking about all the time. That goes in there. Okay, so I'll stop. Thanks.